The preceding lecture covered the statistics used to describe the results from a sample. In this lecture, I'm going to cover the statistics used to assess specific questions that can be framed as hypotheses. Most of these hypotheses are about differences between groups or differences between conditions. Now I turn to a different type of t-test, which again comparing two groups. Now they're paired samples rather than independent samples. And paired samples almost always means that it's the same group. So the scores are paired. So you've got John's score on one measure and John's score on another measure. And you've got Mary's score on one measure and Mary's score on another measure. So this is a situation where you've got two groups that are created by two measures rather than two groups that are entirely independent and are being compared on the same measure. So this is a typical application would be a before and after test. So this is awareness of a brand before a marketing campaign and then awareness of the brand after the marketing campaign, or interest in a product before seeing the ad and interest in the product after seeing the ad. And the value of this t-test is that we have the same people being scored both times, and we can take advantage of the fact by pairing those people up. So if John, for example, uses the high end of the scale, then his difference might be 6 and 7, and if Mary uses the low end of the scale, then her difference might be 2 and 3, and we don't average those scores. We sort of take advantage of the fact that we know who the same person gave us both scores. So a paired samples t-test tends to be more powerful than treating the sample scores as if they came from different samples. So this test is a test of equivalence of two means from the same sample. So it's often also called a one group, two measures test. And the t statistic is the t observed is equal to small d bar, that is the average difference between the scores, minus capital D, which is the hypothesized population difference. And again, that hypothesized difference usually is presumed to be 0, so that will disappear. And divided by the standard error of the mean for the differences, which is the standard error of the differences divided by the square root of n. And it turns out that mathematically the average difference is equal to the mean differences in pretest and post-test, or the mean differences on the two scores. So the average difference is equal to x bar 1 minus x bar 2. So what's different in this calculation is not in the numerator, but it's in the denominator. The s sub d is different from the s sub x bar 1 minus x bar 2. And the degrees of freedom for this test is n minus 1. So you've only got one sample here, n minus 1. Here's an example of a paired samples t-test. We have average salesperson sales before and after some special salesperson training. And we want to compare them at an alpha of 0.05. So we have a sample size of 45, and we see the average sales before is 6,500 units per month, for example, and the average sales after is 7,100 units per month. And we're told that the standard deviation of the difference is 1,210. So we calculate our t observed. Remember, we're hypothesizing no difference, so capital D is 0. The average difference is 7,100 minus 6,500. The standard deviation is 1210, and of course we have an n of 45. So t observed turns out to be 3.32. We compare that to the t critical value for 44 degrees of freedom, which is 2.02. Since the observed t is greater than the critical value of t, we conclude that at 95% confident, we are 95% confident that indeed the sales after the training were greater than the sales before the training. Now we're going to look at comparing two proportions. Recall that earlier we looked at a t-test of a proportion versus a point estimate. So now, just as we looked at, we moved from testing a mean versus a point estimate to looking at the means of two groups. Now we're going to move from comparing a proportion to a point estimate to comparing the proportions of two samples. So these are two independent samples. Again, this is a two groups, one measure comparison. So we've got two groups of people. We're looking at the proportion who give a certain response in each case. And the t statistic is given as, for the observed from the sample data, as the difference between the two proportions relative to the hypothesized differences in the populations. And again, those are usually presumed to be equal, so that disappears, leaving the difference in the two proportions, divided by the standard error of the differences in the proportions. And that expands to P1 minus P2 minus the presumed difference in the populations over the square root of P bar Q bar times 1 over n plus 1 plus 1 over n plus 2. Now, P bar and Q bar are the weighted average proportions. So P bar is n1 times P1 plus n2 times P2 over n1 plus n2. And of course, if n1 and n2 are equal, that turns out to be just the average of the proportions in the two samples. And this t-test requires samples of 30 or more. It turns out that t-tests for proportions are unstable with small samples. We'll illustrate the comparison of proportions from two samples with this example. Compare the success rate of two groups of 50 salespeople. Those with engineering degrees, 12% success, and those with business degrees, a 16% success, at an alpha of 0.05 and an observed standard deviation of the difference in proportions of 0.06. So again, the t is calculated as P1 minus P2 minus the hypothesized difference. In this case, we're not hypothesizing there is any difference. So we're simply asking the question, is the proportion in one group greater than the proportion in the other group? And we calculate the observed t as 0.67. And the critical value of t for alpha 0.05 is 1.96. So our conclusion would be that no, these data do not support the conclusion that salespeople with engineering backgrounds and salespeople with business backgrounds differ in their success rates. It is difficult, statistically difficult, to demonstrate differences in proportions because, well, in this case we don't have very large samples, but typically one needs fairly large differences in proportions to see a statistically significant effect.